Hello YouTube, welcome back to the Blind 75 Challenge. We're still solving one problem per day from the famous Blind 75 list of LeetCode questions. Today we've got another problem that deals with bit manipulation. The question is called number of 1 bits and it asks us this. Write a function that takes an unsigned integer and returns the number of 1 bits it has, also known as the Hamming weight. Note, in some languages, such as Java, there is no unsigned integer type. In this case, the input will be given as a signed integer type. It should not affect your implementation, as the integer's internal binary representation is the same, whether it is signed or unsigned. And also in Java, the compiler represents the signed integers using 2's complement notation. Therefore, in example 3, as we'll see later, the input represents the signed integer -3. So let's scroll down to our examples. We have example 1. It gives us the input, which is 11, and it gives us the output of 3 because it has a total of 3 1 bits. Example 2 gives us a larger number, there's only 1 bit, so that's what we return. And then example 3 has every single bit as a 1 except for 1 value remaining, so of course 32-bit integer, we are left with 31. So there's a couple of ways we can solve this. Let's first look at a kind of naive approach. So what we want to do is obviously keep track of the total number of 1 bits that we have. So we'll define an integer total and set it to 0. Now we want to define a mask. So what we're basically going to do is create a mask. And for now, we're going to set this to 1. And let me just explain what we're going to do. Right now, we've got a 1. So in binary representation, that looks like this, right? It's 32 bits and the final bit is a 1. So what we're going to do is use this as a mask and then AND it with the input that we're given, that is n. So what that does, just as a reminder, it's going to compare the bits from both numbers and then only give us a 1 in a position where there are 2 1s. So if we're given, let's say, 1 as n, we compare 1 to 1, and because there's a 1 in both places, obviously we come out with only 1 bit. So what we can do from there is just iterate over this 32 times, and every single time we make an iteration, we're going to move the 1 bit in the mask up a place. So we're just going to bit shift once to the left. So let's go ahead and set up our for loop. So we'll just do for int I equals 0 while I is less than 32. And then let's increment I every single time we pass through. Next, we want to take care of that comparison between the 2 integers. So we'll just do if n and the mask is not equal to 0. And that is if we found a 1 when we AND them together, we're just going to increase that total. And then we want to take care of that bit shifting on the mask. That is just moving that 1 bit to the left. So we'll just do a bit shift to the left. So that looks like this. We'll do mask equals mask bit shift 1 place. And then finally, we're just going to return the total. So let's go ahead and run that and see what we come up with. And we can see the answer is accepted. But this is still kind of naive, right? Because no matter what happens, we have to bit shift 32 times. So even if the input is a 0 and we know there's not going to be any 1s, or for instance, in example 1, where we've got 11 and we've got 1, 1, 0, 1, and then the rest of them are zeros, we kind of want to stop here, right? We don't want to have to iterate through 32 times. The problem with the efficiency of our code right now is that no matter what we're given, we always have to loop through 32 times. So in the worst case scenario, this is a big O of n time algorithm, which is linear, but also in the best case scenario, it's still big O of n. So let's see if we can cut down and only loop through the amount of times it takes until we're left with zeros. So let's remove the bulk of the middle code right here, and we're still going to keep the total, and we're still going to return the total. But what we want to do now is we're going to modify the input that we're given. So we'll do while n is not equal to 0. And then let's go ahead and AND the input that we're given with a 1. And then if that is not equal to 0, just as before, we're going to increment the total. And now let's take care of the bit shifting. So before we bit shifted that mask, but this time we want to bit shift on n because we eventually want it to equal 0. But what's also interesting is that we are given an unsigned value, so we have to do a little bit of a different bit shift operation. So to bit shift on unsigned values, we have to do the bit shifting with the ternary operator. And the reason for that is just that the double bit shift operator requires a sign extension. So let's go ahead and take care of that. That will look like n equals n bit shift one place. And let's run it again. Great, and we see that our code has passed once again, but this time we're probably not comparing every single bit in that 32-bit integer. We're probably breaking way before and returning that total. So that takes care of another binary question on the Blind 75 challenge. If you're enjoying these videos, don't forget to like this video and subscribe to the channel. I'll be uploading way more of these as we go through the Blind 75 list. And that just about wraps up another video, so I'll see you again tomorrow for another question.